All right, yeah, so I'm going to talk about spin caloritronics, so coupling of spin and heat currents on very short timescales of picoseconds. So all the work I'm talking about was, well, almost all the work was done by Gungman Choi, a former student of mine who's now back at the Spintronics Center in Korea at KIST. And postdoc working with me, Johannes Kimbling, has done a lot of the more recent work. We have a lot of collaborators that help us with samples and various kinds of magnetic characterization and calculations maybe of dynamics and things. And we've been supported by the Army. And actually, Johannes has a fellowship from DFG. All right, so if we go back 30 years, so we've been talking about Spintronics. And this is what Spintronics looked like in 1985 at Cornell. Actually was just starting graduate school, I think, when they must have submitted this paper, Mark Johnson and Bob Silsby. And in this kind of problem, that the spin currents are injected by transporting a charge current across an interface between a ferromagnetic material and a normal metal. In this case, it's aluminum. And then that spin population diffuses and can be detected by modifications of the transport across this other ferromagnetic metal, normal metal interface, in modifying its resistance. Well, okay, so what are we doing now instead, 30 years later, in my group anyway, is to, instead of driving the spin currents with charge currents, we're driving the spin currents with heat currents. And I'll explain why we want to do this very fast in just a minute. But we're generating all the heat by optical light pulses, and we're detecting the spin and magnetization dynamics also optically through magneto-optical effects, both in normal metals as well as in ferromagnetic materials. And you can see the other big difference from 30 years ago is you could publish a PRL with a drawing like this. But now to get something into Nature Physics, you need to make something a lot fancier like that, or the editors won't pay attention to you, right? So, one way to quickly think about it is we're talking about heat. We want to be able to put a lot of power into the system. Most things can't survive for very long at very high amounts of power. But also, we just can get lots of current, heat currents, lots of watts, by taking our energy divided by very short times in order to produce very large heat currents. So mostly in my group, I would say, until maybe 5 years ago or so, we were mostly concerned just with these sort of coefficients that relate heat currents and temperature gradients or temperature differences between different systems. So bread and butter is thermal conductivity, a very important engineering parameter, of course. And we can measure this, in many different ways. So this is the, thermal conductivity. I'm writing as capital lambda is the coefficient that relates a temperature gradient to a heat current in the bulk of the sample. Fourier's law, thermal conductivity as units watts per meter Kelvin. Another parameter that we've studied extensively is the thermal conductance of an interface between two different kinds of materials. That's a linear transport coefficient as well. It's just the transport coefficient that relates to temperature drop at an interface to the heat flux that's passing through the interface, linear response. That has units of watts per square meter per Kelvin. And we've also studied a lot, and you'll see it's very important in this problem, are volumetric heat currents. It's kind of a funny idea, but what we're thinking about here is the exchange of thermal energy between various excitations in the solid. So much studied is the exchange of energies between electrons and phonons. That's an important parameter in all of our modeling in these experiments I'm about to talk about. Or, for instance, the exchange of energy between magnons and electrons. In Alan's sort of picture, I guess, the quasi-particles and the order parameter we think of as thermal baths. And then we can write a coefficient that describes the flow of thermal energy between these thermal baths. And this is just a two-temperature type model, but applied to electrons and magnons instead of electrons and phonons. So enough introduction. Let me just sort of give you an idea of what I want to go through quickly here. I'm just going to go, it'll be easy to remember, I'm going to go from 2 to 3 to 4. So 2 layers. I'm going to talk about a normal metal in contact with a ferromagnetic insulator. We, like everyone else apparently, use YIG to do this experiment, though it would be nice to extend it to some other materials. You know, I'm in a material science department. We like to study lots of things when we can. And what we're doing in this experiment is, we're creating heat with an optical pulse and then measuring spin accumulation in the normal metal by magneto-optic Kerr effect. And the source of spin is an interfacial term in the spin-Seebeck effect. Then I'll talk about 3 layers. Now I'm switching to all metallic systems. But it's basically, I just have a heat source in the platinum, a heat sink of copper, and I'm transporting that thermal energy through a perpendicular ferromagnetic metal. In this case, we're going to measure the spin accumulation in the copper, also by MOKE. And in this case, the dominant signal that we observe, well, both things contribute, but the thermally driven demagnetization can be very important. And then I'll talk about 4 layers where we add another sort of a spin valve structure, where we add another ferromagnetic layer that allows us to kind of integrate spin currents in some sense over short time scales and gives us more sensitivity to the details. And we get a spin transfer torque very clearly coming from the spin-dependent Seebeck effect. That's the differences in the Seebeck coefficients of the different up and down spin channels. Okay, so the basic experiment looks like this. It's a more or less standard pump probe optical measurement. It's actually quite simple by these kinds of things. I'm by no means a laser jock kind of person, but it's a laser oscillator. You buy a titanium sapphire laser oscillator these days for about $100,000. Put it on a table. It's about this big. Split the beam into 2 paths. One is a pump path, which gets modulated at very high frequencies. That turns out to be important to keep the noise very low. It's delayed by a mechanical stage, so it changes the time of arrival between this pump beam on the surface and a probe beam arriving at the surface, which is the other thing that gets split off here. And we can run this in various modes. I don't have all the drawings, right? But we can heat from one side and measure from the other side. We can measure reflectivity, so we measure intensities. That has to do with phonon temperatures usually. And most important for this talk, we can also split off the beam and analyze the polarization of the reflected light, in a simple beam splitter, polarizing beam splitter and balanced detector setup, and measure magneto-optic effects with extremely low noise and high sensitivity. And typically it's relatively crude magnetic work. We're just using a little permanent magnet to change magnetic states, flip things just by flipping this magnet, very simple structures, okay? Just small permanent magnets. Okay, so let's get the first topic. So the first topic is this, picosecond spin-Seebeck effect. So I have a normal metal on top of a YIG layer on top of a GGG substrate. Our samples have come from couple different locations, but think of this as kind of, it's opaque, but it's 50 nanometers thick or so, or 60 nanometers thick. This is about the same order, and then it's on a solid substrate. And if you think about just thinking about the thermal circuit, so where does the thermal energy go in this system? Well, the laser pulse comes in, it heats the copper electrons. That's where the energy enters the system. And the energy then gets all over, goes everywhere else, right? It couples mostly to the copper phonons. That's the strongest direction that the heat will flow. And then eventually that'll couple to the phonons in the YIG, through an interface conductance, and the heat will diffuse out, right? So both of these things, this is just a very simple overview of it. Of course, these things are all diffusive as well, is how we model diffusion in both systems. Now, what we're interested in here, actually, there's some unknowns, right? And we have to make maybe some guesses. So if one of the things we're interested in is, okay, what's the thermal conductance that connects these copper electrons and these YIG magnons? So there should be something like a Lorentz number, maybe, that relates this spin mixing conductance to a thermal conductance. And then there's some sort of volumetric thermal conductance that connects the magnons to the phonons in the YIG. This is actually, don't think has really been measured. Of course, it's just a kind of a parameter that would average over a hugely complicated problem, because you don't know which phonons are interacting with which magnons and how all that would actually happen in the system.
Why don't you put in a copper electron to YIG phonon?
Good. That's actually in sort of my world of sort of like heat transport physics. A lot of people care a lot about that. We don't have any evidence that this is important in anything we've ever studied, but it doesn't mean it's not there, right? Yeah, so yeah, it could be there. I mean, you could think of, yeah, there's also, you know, in principle, there's this too, right? So,
Yeah.
right? Okay, so let's think about some of the numbers. They're a little hard to compare because they have different units, but a typical electron-phonon coupling in copper is on the order of 10 to the 17 watt per meter, cubic meter per Kelvin. Okay, it seems like a ridiculous unit. You've got, I don't know. I mean, but it's, but you can see if you kind of go down to cubic microns, it starts to make into sort of watts kind of numbers, right? So that's per Kelvin, watts per Kelvin. The magnon-phonon coupling, sorry, the spelling error. No, coupling's okay. We have never measured it in YIG, but we have measured it in a cuprate spin ladder. And the way we did that is because a cuprate spin ladder has a very high magnon thermal conductivity, and by working at very high frequencies, we can start to separate the magnon and phonon temperatures, and we've published this before in one of these telephone number compound cuprates. Okay, and so that in our experiment at room temperature in a cuprate spin ladder, that's how big that number is. So it's more than an order of magnitude smaller than an electron-phonon coupling, but still quite large. It's a big number in this business. This is about how big a phonon-phonon interface conductance is. And if we make a kind of, I'm going to show you that this is what we measure for this kind of the transport of the Seebeck effect at the interface. If we just kind of think about multiplying that by a thermal voltage, we get something like 2 megawatts per square meter per Kelvin. So orders of magnitude smaller than the phonon-phonon coupling and relatively weak. So there's not much energy going directly into the magnons. This is sort of equivalent to writing a spin mixing conductance times a Lorentz number here, a Sommerfeld-Lorentz number. All right, so what does this kind of look? What is the order of our analysis? So first we solve the heat problem, right? And we do that by solving the two-temperature model in copper, and we couple it to phonons in YIG. This is just the two-temperature model in the copper. I'm not writing the equations for the YIG. But this is just a model calculation of what our experiment would look like. So we heat the copper with a pulse of light up. It takes about a picosecond. The light turns off after about a picosecond. The copper electrons cool on something like a picosecond time scale due to the electron-phonon coupling. So now the electrons and the phonons in the copper are in equilibrium. There's still a big temperature drop between the copper system and the YIG system because of this interface conductance. And it takes some time for this copper to become in equilibrium with the YIG. It takes hundreds of picoseconds. So there's a sizable temperature drop that exists for some time, on the order of 100 picoseconds or so. All right, so that's the thermal problem. And then we have to solve the spin problem. And we do it a completely diffusive equation. We solve for the spin chemical potential and let the spin chemical potential diffuse. But OK, so what are we parameterizing? Basically, we're just parameterizing what we picture as something like a spin flip process. The YIG is magnetized normal to the surface, and we're detecting the normal component of magnetization that develops in the normal metal from this temperature difference between the metal and the YIG. And we really just kind of parameterize it. So this is the spin current we write as a spin mixing conductance and then some units. This is a Seebeck coefficient for this process and the temperature difference between the electrons in the normal metal and the magnons in the YIG. Okay? And then even more, I even parameterize it further, and I just write all this stuff in front of the temperature difference as alpha. Okay, so that's just the coefficient that relates the spin current to the temperature difference. And that's all we can really measure. So I'm just going to only talk about that. If you go into a microscopic picture, based on like what Yaroslav has written down and other people, this coefficient here should be something. I mean, all Seebeck coefficients have to be something times K Boltzmann over E. It has to always be, in terms of volts per Kelvin, if that's the units we're using. And so then this thing is dimensionless. And this looks like, I guess, a magnetic moment of an electron divided by some like magnetic moment of a coherence volume of the YIG. Something like the magnetic moment of a unit cell or something like that. Okay? Anyway, so we then solve for spin currents, which are just gradients in spin chemical potentials. Spin chemical potentials evolve, this is just the divergence of the currents, and there's a relaxation time, which is a parameter. So really, to fit the experiment, I have two parameters. I have this coefficient that describes the generation of spin current, and I have a relaxation time, which describes how fast the spin disappears from my problem in the experiment. And that's it. That's what the data look like. That's what the sort of the fits look like. This particular example is 60 nanometers of gold on 20 nanometers of YIG. And it's done at different temperatures, from room temperature approaching the Curie temperature. So we've done this in a lot of different ways, but this is kind of a nice example. This is the magnetization that develops in the gold due to the spin transport into the gold, which we detect due to the magneto-optic Kerr rotation. So this is basically just a Kerr rotation, which has been converted using a coefficient that we've determined in other experiments. Right? So there's a coefficient that relates magnetization to Kerr rotation in gold. It's about 50 nanoradian per meter per amp. And this sort of noise level down here corresponds to Kerr rotations on the order of something like 10 to the minus 8 or a few times 10 to the minus 8 radians. And these are the parameters from these fits. So on the black symbols are the values of this coefficient alpha. They're on the order of 10 to the 8. They get smaller as you heat it up. And this is a spin relaxation time. It's on the order of a picosecond, and it has big giant error bars as you make it hotter, so we can't really determine it. But that's the sort of orders of magnitude of those two parameters. Huh?
So you're not sensitive to magnetization of YIG in the
the gold is opaque. Yeah.
These thicknesses.
It's sufficiently opaque that we don't see the YIG magnetization. Now, if we make the metal layers thin, then yes, we pick up signals from the YIG. Yeah, absolutely, right. But we don't really, anyway, the wavelength is near infrared, so it's 800, Ti-sapphire laser operates at 800 nanometer. Yeah. Okay, and if you look at longer times, and again, this is maybe a different sample even. This is copper, copper on YIG. If you go look at this on a logarithmic timescale going all the way out, the red is the delta T, the signal is the open circles, and you can see it's basically consistent all the way out as the system cools. And the important thing about this is basically we don't see any sign of a temperature gradient in the YIG generating a significant signal in the measurement. In other words, we're only seeing the temperature difference at the surface. We don't see any gradient in the sample. That's so far, right? So we'd like to be able to do that, but so far that's what we've got. All right, that's kind of the end of the story. We'd like to have more systematic variations of samples. We'll work on that. As kind of a material scientist, we'd really prefer to, vary the quality of the interface in some way or prepare it in different ways systematically. But we can make some conclusions. We don't see any real thickness dependence. We don't see any metal thickness dependence. We certainly get larger values for copper than we do for gold. If we form the interface in situ in the deposition chamber, we get a better coefficient than if it was formed ex situ. And that's what those numbers tell you.
Remind me which one was alpha?
Alpha is the coefficient that relates the spin current to the temperature difference.
Okay.
Yeah. Yes.
So how does it compare with the results by Darcy Ho from the Cycle group?
I don't know, honestly. I don't know whether anybody can say it's coming from this interfacial term.
No, but okay.
Right.
They're of course much smaller delta T, I see.
Yeah, and I don't know if is it quantitative what they did? I mean, don't they always get there's always this uncertainty in some inverse spin Hall angle or something, right?
That is indeed.
Right. Right. So, I think one of the things we feel like is a real advantage of this approach is we can be quantitative. We know what the number is, right? And you could ask the question a little differently. How does that coefficient compare to that sort of microscopic picture? It's consistent with it, right? If you take spin mixing conductances and multiply it by these other factors, it's sort of reasonable, right?
It's independent
independent of thickness for what thicknesses?
Very small range of thicknesses right now. I think YIG thicknesses only go from 100 to 20. Right, so we haven't looked at thicker ones yet, or up to 100 nanometers. Yeah, yeah. Right. Okay. So now I'm going to switch gears. So I want to now add, I want to go to metals now. So now I'm going to. This is a 3-layer metal structure. Place a perpendicular metallic ferromagnetic material in between a platinum heater and a copper heatsink. So again, we're heating the platinum, and now we're measuring. Actually, the probe is measuring the other side of the sample. Right? There's a sapphire substrate up here. The pump's coming through the substrate, heats the platinum, heats the magnet. The heat goes into the copper. We measure spin in the copper by the same technique. Right? And we've studied different metals. These are multi-layers to make perpendicular magnetic anisotropy in the thing. And we attribute the spin generation to 2 mechanisms. Again, we're thinking about the problem very sort of thermodynamically, very in terms of heat baths and heat currents. And so if we think about there's a term that generates spin, which is the exchange of thermal energy between the electrons, the quasiparticles, and the magnons, or the order parameter, right? We're heating the electrons, the heat goes into the magnons. The magnons heat up, and due to essentially angular momentum conservation, they dump spin back into the electronic system, so the quasiparticles. Okay, so that's the picture. There's also spin loss. I'll show that in a second. And then we say there's also a spin-dependent Seebeck effect. So if there's a heat current passing through a ferromagnetic material, it generates a spin current, which has the consequence of basically, in a good approximation, as being a source of spin at the interface between the ferromagnetic material and the normal metal. And this is sort of what you can write down. It's just fundamental units. There's a coefficient, which is now the spin-dependent Seebeck coefficient, and a heat current. If you drive it in this way, you can relate it to heat currents and spin currents at the interfaces. Now, it turns out this is one of the things, so Johannes Kimmeling, working with me, is a very rigorous guy, and is going through all the sort of calculations and how we're doing things and improving it. And one of the things he really implemented was just go ahead and create a full model of the spin generation in the ferromagnetic material due to the gradients of the chemical potential, take into account the gradients of chemical potential in the ferromagnetic material, not just treat it as a surface. Anyway, so it's a little bit complicated, but it's just the same equations. Spin currents are generated by Seebeck coefficients, and gradients in chemical potential. The diffusion equation for the spin chemical potential is there. Now note that it turns out that, okay, we don't have pure spin currents, but it's basically an open circuit device, and it turns out that the charge currents are really negligible. They're orders of magnitude smaller than the net spin currents, right? So this is a very good approximation that the total currents are 0, right? Okay, so we zero charge current. Now what I've written down here is that the temperature of the spins are the same for both up and down. And I'm going to come back to that later, because that turns out that's the assumption that we made before, and I think most people have made in these kinds of problems, but it's not easy to justify that assumption. All right, so and what happens? And then, okay, there's some details in the notations that we got to deal with. Okay, so again, how does the experiment proceed? In the modeling, we measure the magnetization dynamics using MOKE. So this is just an example of what happens to the magnetization of these thin 3 nanometer thick ferromagnetic layers that are being heated remotely from the platinum. So we heat the platinum with an optical pulse. Those hot electrons heat the magnet. While the electrons are out of equilibrium with the phonons, it demagnetizes a lot, and then it recovers because the magnetic temperature drops back to where the phonon temperature is. And so the magnetization, it demagnetizes and it recovers, all in a couple picoseconds. If I take the derivative of that magnetization, it basically just has 2 lobes. There's sources of spin, in one direction, and then it recovers and comes back out the other way, right, due to the magnetization. And we can also measure temperatures, due to this thermoreflectance technique that we've worked on for a dozen years. And that's the examples of the data here. Here's the phonon temperature of the copper Here's it's kind of a mixture of electrons and phonon temperatures of the platinum is up here. And this is the temperature of the magnons or electrons in the ferromagnetic layer, right? And this is modeling. There's parameters that we measure in other experiments. There's some parameters which get fit to make this look good here, that kind of thing. But those are mostly like electron-phonon couplings and thermal conductivities of this layer and things like that. All right. So there's a lot of different transport coefficients that go into the calculations to make this whole thing work. Many of them are constrained in various ways that I don't have time to go into. Okay, so then we measure the spin accumulation in the copper side with MOKE measurements, and we compare it again to spin diffusion models. So just as we did before, we have a spin diffusion model for each layer in the material that has source terms and sinks and transport, diffusion constants, and that's the end result of the model. So here's the data. So this is the Kerr rotation directly. I haven't turned it to a magnetization in microradians. And for two different ferromagnetic layers, this is this arrival of spin, and then it goes back. And there's a small offset here, which is blown up here. And you can see the sort of noise. This is 10 to the minus 7 radians. The noise is maybe on the order of 10 to the minus 8 radians. That's what, with some signal averaging. 10 to the minus 8 radians is a person standing on the moon. That's the angular size, okay? And actually, so then what you get out of this, you fit things. So we fit spin relaxation times, we fit Seebeck coefficients. We also have to get the amplitudes right from the the coefficient relating Kerr rotation and spin coefficient. And I'll give you the numbers in a second, but I just want to just show 2 slides, and I'll give you the numbers. So so this is just the 4-layer structure. I don't have a lot of time. So platinum, perpendicular magnet, copper. Now add a ferromagnetic layer that is perpendicular to the source of spin, and that serves as a detector for the spin. So as spin is absorbed by this, it gets kicked out of plane and then precesses, right? And so there's a spin torque that's transferred to this other magnetization, and you just do basically all the same things. But now I have a third differential equation to solve. So I have all the heat differential equations to solve, and then I have to solve all the spin diffusion equations, right? And then I have to solve the magnetization dynamics equation, right? And you put those 3, and luckily they're not coupled to each other, right? In other words, the spin flow doesn't carry significant amount of heat, and the magnetization dynamics doesn't have a big back action on the spin, right? So we don't think we have to couple the differential equations. They can be solved separately. And this is the result, right? This is calculations of spin currents. This is the fitting to the experiment for the 2 different metals, right? Okay. And of course, you fit damping parameters, you fit frequencies, all that. But they're very, very standard sort of values to all this. Okay, so what do you get? Yeah, well, you get some numbers out of this problem. So this is from our earlier work where I'm just trying to make sure I keep track of how much things have changed when one person does the analysis versus another person does the analysis. Always a kind of a dangerous activity. But it's pretty good. It's pretty good. This is the spin accumulation experiment. This is the precession experiment. And you can see the numbers agree pretty well. We get spin relaxation times on the order of 20 femtoseconds in this material, 100 femtoseconds in the cobalt nickel. This coefficient for the spin-Seebeck coefficient is both times about 20 microvolts, but the sign changes, right? And you can see that in the raw data, actually. You can see the direction that this goes initially is different, right? And the amplitude is smaller because the effects are competing with each other.
Sorry, how do you measure temperature profile in the structure? How do you know the...
Yeah, that was sort of this kind of experiment. So we measure the platinum temperature. We can measure the copper temperature.
You measure the temperature of the whole layer?
You measure it within an optical absorption depth.
Okay.
Right. And then we do modeling to sort of get the temperatures. I mean, there's not much of a this kind of structure, there's not much temperature gradient in the copper. It has a huge.
So you know, like electron temperature in copper. You know also phonon temperatures.
Yeah, we put the phonons in the model too. Everything's in there.
You know temperatures of electrons, temperatures of phonons.
Right, and temperature of magnons. Right. Well, temperature of the magnetic temperature. Right. We don't consider like a magnon thermal power or anything like that in this experiment.
Well, you interpret it as
spin-dependent
Seebeck. You know the
coefficient.
temperature of magnons.
Right, right. Now what we don't know, and that's actually sort of my next point, what we don't know, we've always, when we analyze what I just showed you, we've assumed that there's an equal temperature for up and down spin channels. Right? That's right. Probably not, we think. We don't think there's enough scattering between the spin channels to keep them at the same temperature.
Just electron scattering.
But not if you're close to the Fermi level.
So that would be
You know,
by Van, right? They're quite significant.
yeah, this is called, the people who study this call it spin heat accumulation, right? It's a,
That's very.
anyway, I think we need to go through the numbers maybe more carefully, but I mean, it's Fermi, Fermi liquid, right? If you're near the Fermi level,
So what's the temperature?
the electron-electron interactions are weak, right?
What are the temperatures?
These are room temperature.
Okay, and the gradients are small.
Yeah, the gradients are small,
Okay.
a few Kelvin. Right?
Well, then it means that the temperature of individual electron species is also ill-defined. It's like
Yeah.
electrons are
right.
free particles, so
You
there's
say, well,
there's no
you can't even
temperature.
talk about it as a
It's not
temperature.
temperature. There's some kind of effect that maybe.
Right,
It's
I
just
think
a-
it's,
Yeah, that's
Just
called
the-
an effective temperature, which is a fit of a non-equilibrium
Non-equilibrium
function. But
distribution.
the fact that these
Right.
distribution functions are very different, I think it's
But it
even a
can't-
room temperature.
If you have an I agree with yours. If you have an electron temperature, it's the same for both.
right, right. Okay, you're saying if you're going to define a temperature rigorously, you'd say that's okay.
Kinetic equations and fit the non-equilibrium distribution functions with some sort of effective
But the
distribution, and this has nothing to do with the equilibrium temperature. It's just a parameter to sort of fit the thermal smearing or the smearing of the whole distribution. It's just an efficient parameter which people have calculated that in spin system and other systems, and it is a very good fit parameter to the real distribution.
Sure, it's another fit parameter.
But but experimental.
To calculate that, but
Right.
I think that.
But experiments have only
clearly
normally probed.
There is a giant magnetic heat resistance in spin valves.
Yeah,
And
we've
this
done,
can
we've
only
measured it.
exists
Right.
if you have
Right.
these non-equilibrium temperatures.
Well, yeah.
okay, near an interface.
I mean,
Near an interface, you mean? What in a spin
you have a
accumulation?
you have a spin valve, and you can sort of calculate, you can measure
Yeah.
the heat conductance, and you see that it's significantly different from here to there. And you can also sort of measure the distance dependence in the spacer.
Yeah, but I'm not sure if that's a proof of spin heat
That
accumulation.
Yeah, it's not.
No,
Yes,
if
it
you
is.
include magnons, you don't need spin heat accumulation.
Exactly, yeah. It's the whole theory disregards magnons, and the magnons could be dominating.
Actually, I think it may not even be that complicated. but
Electrons, but with magnons only.
I think people want their coffee break. Let me. Yeah, let me just finish. I only have a couple slides. So basically, okay, so with all the caveats we've just talked about, how do you actually do this? But okay, just say you're going to add another temperature, spin up and a spin down temperature, right? Well, it turns out then you also have to start talking about the spin up and well, you have this in there anyway, the spin up and spin down conductivity. If we apply a Wiedemann-Franz law to that, you can also just sort of convert it to an asymmetry in the thermal conductivities of the channels, right? And then you can rewrite this spin current in terms of asymmetry parameters. So how asymmetric are the Seebeck coefficients and the thermal conductivities, as well as the instantaneous heat currents that are being carried by the different channels, right? And it turns out this is really gets to be a very complicated phase space of parameters to think about. But one of the things we're thinking about, well, if this is actually true, if you really did have spin heat accumulation, different temperatures for the spin up and spin down channels, it could actually help you generate more spin current in these kinds of experiments. And this is just a kind of a proxy for the efficiency of the process, where we're integrating the spin current that's generated over time, and you get a certain thing in certain units. And this just says, well, if I make the thermal conductivity have an asymmetry that has the opposite sign of the asymmetry in the Seebeck coefficient, you can get larger effects. This is basically what this tells you. Okay, so let me summarize. So on picosecond timescales, we can isolate the interface term to the spin-Seebeck coefficient, or at least that's only things that we seem to be sensitive to. The order of magnitude is consistent with theory, order of magnitude, I think, with theory. All right, and and other measurements of spin mixing conductance. If we switch to the metallic structures, we have different mechanisms that contribute more or less of the same magnitude in our experiments, but they actually can have different signs. And so, in one case, they actually add together. Those two mechanisms reinforce. But about the largest tilting we've observed in this experiment is about 1% change, shift tilting of the magnetization of the spin valve structure. And that's using heat currents that approach 100 gigawatts per square meter or something on that order. This spin-dependent Seebeck coefficient can be measured accurately in this kind of measurement that we're using, particularly with the spin valve structure. But I would say it's really very difficult to relate that coefficient to microscopic parameters, partly because of these, you're not sure about a lot of this asymmetries in the various transport coefficients, and we're not sure about these ideas about are the temperatures the same or not. All right, so thanks.
Okay, first question.